What the hell is up, you glorious bastards? Back for more punishment or yeah. Welcome back to the Deep Dive, where we shove a fire hose of knowledge down your throats and hope you don't drown. Today, we're going to tackle those little silicon bastards, known as GPUs. You know, the things that make your games look like a goddamn Michael Bay film and your computer run faster than a squirrel on meth. But let's be real for a sec. If you're a total noob and you've never even heard of a GPU, just picture it as like a brain on roids for your computer. It's like pumping iron and doing calculus at the same damn time.
That's certainly one way to visualize it.
So let me ask you, dear listener, do you actually know what GPU stands for?
Oh.
Don't worry, I won't judge you if you don't. Hell, I probably didn't for the longest time either.
Well, it stands for Graphics Processing Unit.
See? You're already learning shit. Now, to help us break down these silicon savants, we've got a real brainiac here today. A goddamn wizard when it comes to GPUs.
Happy to be here.
All right, let's get this party started. According to our good friend Wikipedia, a GPU is, and I quote, a specialized electronic circuit designed to rapidly manipulate and alter memory to accelerate the creation of images in a frame buffer intended for output to a display. Basically, it's the engine behind all the pretty pictures on your screen.
That's a somewhat simplified explanation, but you're not entirely wrong. Originally, GPUs were all about processing images, making those computer graphics look all sexy and shit. But over time, they've become these parallel processing powerhouses, crunching numbers and tackling all sorts of complex computations.
Kind of like those scrawny kids in high school who hit the gym and came back looking like fucking Greek gods.
I suppose that analogy works.
And get this, GPUs have been kicking ass longer than some of you asshats have been alive. We're talking way back to the glory days of arcade games. The frickin' 70s, baby. Remember those pixelated masterpieces like Pac-Man, Space Invaders, and Galaxian? Those were all running on custom graphics chips that were basically the granddaddies of the GPUs we know and love today.
Ugh, the golden age of arcades. Those early systems were surprisingly innovative. Take the Williams Electronics games from the early 80s like Robotron 2084, Joust, and Bubbles, for example. They used custom blitter chips to create some really groundbreaking visuals for the time. These chips were essentially specialized circuits designed to copy and manipulate graphical data very quickly.
So they were like tiny digital artists slaving away to make those blocky characters move around the screen.
That's one way to think about it.
It's insane how far we've come since then.
Yep.
Back then, just getting those pixels to move was a goddamn technological miracle. And then, bam, 3D graphics hit the scene, and gaming was never the same. It was like going from watching a shadow puppet show to being thrown headfirst into a goddamn Avatar sequel.
The transition to 3D graphics was indeed a significant leap forward. As with 2D graphics, the arcade industry was once again at the forefront of this revolution. Systems like the Namco System 21, which was used for the amazing racing game Winning Run, and the Taito Air system, used dedicated polygonal 3D graphics boards. These early systems paved the way for the immersive 3D gaming experiences we enjoy today.
Speaking of 3D graphics, we got to give a shout out to the OG 3D accelerator, the 3DFX Voodoo. That shit was revolutionary back in the day. It was like strapping a rocket engine to your PC. I remember drooling over those cards in magazines, just dreaming of the day I could afford one.
The 3DFX Voodoo was undeniably a game changer. It provided dedicated 3D acceleration that was far superior to anything integrated solutions could offer at the time. It was a crucial step towards the powerful and programmable GPUs we have today.
So we've gone from blocky sprites to photorealistic worlds, and it seems like GPUs were the driving force behind the whole damn thing. Pretty mind-blowing, right? But here's the kicker. GPUs aren't just about making things look pretty anymore. They've become these number-crunching beasts, capable of tackling some seriously complex shit. We're talking about GPU, general-purpose computing on GPUs. It's like using a Ferrari to deliver pizzas.
That's an interesting analogy. Not entirely inaccurate either. GPU is all about leveraging the parallel processing power of GPUs for tasks that go beyond graphics. This has opened up a whole new world of possibilities. Scientists are using GPUs to run complex simulations, engineers are using them for design and analysis, and even financial analysts are using them to try to predict the stock market.
So these little bastards are doing everything from modeling climate change to figuring out which meme stocks are going to the moon next. Fuck me.
Well, maybe not everything, but their impact has been significant across many fields.
All right, I'm starting to feel a little out of my depth here. Let's break this down a bit. How the hell do developers actually use GPUs for all this crazy shit? Do they have some secret handshake or something?
That's where programming models like OpenCL and CUDA come in. These frameworks give developers the tools to write code that specifically targets the parallel processing capabilities of GPUs.
So it's like giving them a special language to communicate with these number-crunching beasts.
I could say that.
This is getting seriously deep, even for me. But you know what's even more fucked up? Your phone probably has a GPU that's more powerful than a supercomputer from a few decades ago. We're carrying around pocket nukes in our pockets.
That's true. The miniaturization of technology has been quite remarkable. And it's not just about raw processing power. Energy efficiency is becoming increasingly important, especially for mobile devices and those massive data centers that power the cloud.
Yeah, because nobody wants their phone turning into a goddamn hand warmer or their electricity bill looking like the national debt. But all this talk about energy efficiency makes me wonder about the environmental impact of these power-hungry GPUs. Have you seen the amount of energy those crypto mining farms consume? It's insane. I mean, are all these technological advancements really worth it if we're going to fry the planet in the process?
It's a valid concern. The environmental impact of technology, especially energy-intensive operations like cryptocurrency mining, is a complicated issue without easy answers.
All right, let's not get all preachy here. We're here to learn about GPUs, not solve the world's problems. But it's definitely something to think about, right? Anyway, we've covered a lot of ground today, folks. From those humble beginnings in arcades to the mind-blowing world of GPU, it's clear that GPUs have come a long way. But we're just scratching the surface here. There's a whole lot more to explore. So stay tuned for part 2 of our deep dive into the world of GPUs, where we'll delve into the different types of these silicon badasses and what makes them tick. Until then, stay curious, you magnificent bastards. All right, you glorious pixel pushers, welcome back to the deep dive. Last time, we took a wild ride through the history of GPUs, from those smoke-filled arcades to their current status as the backbone of, well, pretty much everything. We even talked about those brainy bastards doing some serious heavy lifting with GPU. But hold on to your asses, because we're about to go even deeper down the rabbit hole. Today, we're going to dissect the different types of GPUs out there and try to figure out what the hell makes them tick.
Sounds like a plan.
All right, let's cut the crap and get to the good stuff. We've got integrated GPUs, dedicated GPUs, and then those weird hybrid things. What the fuck is the difference between these bad boys? It's like trying to choose between a tricycle, a monster truck, and a freaking Segway.
Well, imagine your computer is like a city. The CPU is the city center where all the big decisions are made and all the paperwork gets shuffled around.
Okay, I'm following you so far. So where do these integrated and dedicated things fit into this city analogy?
An integrated GPU is like having a small graphics department right inside City Hall. It's convenient, it's cheap, but it's not exactly a powerhouse. It shares resources with the CPU and relies on the system's RAM for memory, which can be a bottleneck.
So it's like trying to run a goddamn Hollywood studio out of a broom closet.
Pretty much. Now, a dedicated GPU, on the other hand, that's like having a massive, state-of-the-art graphics studio built right next door to City Hall. It's got its own team of processors, its own dedicated high-speed memory, and it's ready to handle even the most demanding visual tasks without breaking a sweat.
So if you're just browsing the web, checking emails, and watching cat videos, an integrated GPU will do the job. But if you want to crank up the graphics settings in your games, edit 4K video, or do some serious 3D rendering, you're going to need a dedicated GPU.
Right, exactly. It's all about matching the tool to the task. If you're just puttering around town, a bicycle will do. But if you want to win the Indy 500, you're going to need a goddamn race car.
Okay, that makes perfect sense. But what about those hybrid graphics cards? They sound like they're trying to be all things to all people, like a Swiss Army knife. Are they any good, or are they just a bunch of bullshit?
Hybrid graphics cards are an interesting attempt at compromise. They're like having a small graphics studio that can borrow resources from City Hall when needed. They have a small amount of dedicated memory on the card, but they can also tap into the system's RAM when things get heavy.
So they're like the middle child of the GPU world, trying to get the best of both worlds.
You could say that. They're more affordable than dedicated GPUs, but they offer better performance than integrated solutions, especially for casual gaming and light multimedia work.
But let's be real. Nobody wants to settle for mediocrity, right? If you're serious about your graphics, you're going to go for the dedicated option.
Yeah.
It's like the difference between having a quickie in a porta potty and having mind-blowing sex in a penthouse suite.
I'll leave the colorful analogies to you. But yes, dedicated GPUs offer the best performance, particularly for demanding applications.
All right, so we've got integrated, dedicated, and hybrid. Are there any other types of GPUs lurking in the shadows? Don't tell me there are some top secret military GPUs that can, like, render the future or some shit?
Well, there are specialized GPUs designed for specific tasks, like those used in workstations for professional 3D rendering or in data centers for high-performance computing. And of course, you have the mobile GPUs found in smartphones and tablets, which are optimized for power efficiency and performance in a smaller form factor.
Right, because nobody wants their phone turning into a supernova while they're scrolling through TikTok. So it seems like there's a GPU for every occasion, like a different flavor ice cream. But how the hell do we choose the right one? What the fuck do all those specs actually mean? I'm talking about clock speeds, core counts, memory bandwidth, all that gibberish.
Understanding GPU specs can be a bit daunting at first, but don't worry, we'll break it down for you. Let's start with clock speed, which is essentially the heart rate of the GPU.
So the faster it beats, the more data it can pump through its veins.
Exactly. Clock speed, measured in megahertz or gigahertz, tells you how fast the GPU's core processors are running. A higher clock speed generally means faster processing, but it's not the only factor that determines performance.
Right, because you can have a heart that's beating like a hummingbird, but if your arteries are clogged, you're not going to get very far. So what else do we need to consider?
Another crucial factor is the number of processing cores. These are the tiny workhorses that do the actual calculations. More cores generally translate to more processing power, especially for tasks that can be easily parallelized.
It's like having an army of tiny robots working together to build a skyscraper. The more robots you have, the faster the building goes up.
Precisely. But just like an army needs supplies, GPUs need memory bandwidth to keep those cores fed with data. Memory bandwidth, measured in gigabytes per second, refers to the speed at which data can be transferred between the GPU's memory and its processing units.
So it's like having a wide, multi-lane highway leading to the construction site. The wider the highway, the faster the trucks can deliver materials to the robots.
Exactly. And just like there are different types of highways, there are different types of GPU memory, each with its own performance characteristics. GDDR5 and GDDR6 are the most common types found in dedicated GPUs, offering high bandwidth and relatively low latency.
Okay, so we've got clock speed, core count, and memory bandwidth. Anything else we need to worry about? Don't tell me there's some secret government spec like quantum entanglement factor or some shit that we need to consider.
Well, there are other factors like the size of the memory cache, the architecture of the GPU, and the manufacturing process, all of which can have an impact on performance. But for most users, focusing on clock speed, core count, and memory bandwidth will give you a pretty good understanding of a GPU's capabilities.
All right, let's wrap up this tech talk before our listeners' brains start leaking out their ears. We've covered a lot of ground today, folks. We've explored the different types of GPUs and even delved into the murky depths of their specs. But here's the bottom line. GPUs are fucking amazing. They're the unsung heroes of the computing world, powering everything from our favorite games and movies to groundbreaking scientific discoveries. And as technology continues to advance, GPUs are going to play an even bigger role in shaping the future. Who knows what crazy shit we'll be able to do with these parallel processing powerhouses in the years to come. Hey, that's a conversation for another day. For now, let's take a break and give our brains a chance to cool down. We'll be back next week with part 3 of our deep dive into GPUs, where we'll explore the future of these silicon bad boys and what it all means for you.
Until then, may your frame rates be high and your temperatures low.
What's up, you silicon junkies? Welcome back to the deep dive. We spent the last 2 episodes knee-deep in the guts of GPUs, from their pixel-pushing infancy to their current reign as the undisputed kings of parallel processing. We talked about those integrated wimps, those dedicated beasts, and those hybrid weirdos trying to have it both ways. We even dove headfirst into that alphabet soup of specs, trying to make sense of all those clock speeds, core counts, and memory bandwidths. But now, it's time to get existential, folks. Let's talk about the future. What's next for these silicon savants? Are they going to keep evolving, or are they going to hit a wall and go the way of the goddamn dodo?
Well, that's a question that keeps a lot of us up at night, even those of us who eat, sleep, and breathe this stuff.
All right, let's cut through the bullshit. What are the big trends that are going to shape the future of GPUs? Are we talking about some crazy sci-fi shit like holographic displays and sentient AI running on GPUs? Or are we going to be stuck with those, incremental improvements like slightly faster clock speeds and a few more cores?
There are a few key trends that are already shaping the landscape, and they'll likely continue to do so in the coming years. One is miniaturization. We're talking about cramming more and more transistors into smaller and smaller spaces, pushing the limits of what's physically possible.
So it's like those Japanese capsule hotels. cramming as many people as possible into tiny little spaces. But instead of claustrophobic tourists, we're talking about billions of transistors, all working their asses off to make those games look even more ridiculously realistic.
That's a rather colorful analogy. But yes, the trend towards smaller, more power-efficient chips is driven by the demand for mobile devices, wearable tech, and even those data centers powering the cloud.
Right, because nobody wants to lug around a phone the size of a goddamn brick or get an electricity bill that could bankrupt a small country. But there's got to be a limit to how small you can make these chips, right? I mean, you can't shrink a transistor down to the size of an atom, can you?
There are physical limits, of course. But researchers are exploring new materials and manufacturing processes that could push those limits even further. We're talking about things like nanowires, carbon nanotubes, and even graphene. Graphene in particular has the potential to revolutionize the semiconductor industry.
Okay, hold on a second. Let's not get too technical here. I'm starting to feel like I'm back in high school physics class. And that wasn't exactly my finest hour. Can we bring this back down to earth a bit?
Sure. The main point is that the relentless drive for miniaturization will continue to push the boundaries of what's possible with GPUs. We'll likely see smaller, more power-efficient chips that can deliver even better performance than today's top-of-the-line models.
Okay, that makes sense. Smaller, faster, more efficient. Got it. But what about new features? Are we going to see any mind-blowing new tech that'll change the game entirely?
One area where we're likely to see major advancements is artificial intelligence. GPUs are already playing a crucial role in training and running AI models, and that trend is only going to accelerate. We're talking about more sophisticated neural networks, more realistic virtual assistants, and maybe even those sentient AIs you mentioned earlier.
Whoa, hold on a sec. Sentient AIs. That sounds like some Terminator shit right there. Are you saying our GPUs are going to become self-aware and decide to wipe out humanity?
Let's not get ahead of ourselves. Sentience is a complex topic, and we're still a long way from truly understanding it. But it's clear that AI is going to play an even bigger role in our lives, and GPUs will be at the heart of that revolution.
Okay, I'm getting some serious Skynet vibes here. But let's move on before I start stocking up on canned goods and digging a bunker in my backyard. What else is on the horizon for GPUs?
Another exciting area is the development of new architectures, specifically designed for AI and machine learning. Traditional GPUs are optimized for graphics processing, which is very different from the kind of computations needed for AI. We're starting to see specialized AI chips emerge. Chips that are purpose-built for these tasks, with different memory hierarchies, interconnect structures, and even new types of processing units.
So it's like comparing a brain surgeon to a heart surgeon. They both work on the human body, but they have very different tools and techniques.
Exactly. And just like medical science is constantly evolving, so is the field of computing. We're seeing a convergence of different technologies with GPUs, CPUs, and specialized AI chips all working together to create more powerful and intelligent systems.
Okay, my brain is starting to melt a little bit here. Can we bring this back down to earth and talk about what all this means for the average person? Are we going to see some crazy new gadgets and gizmos that make our lives easier? Or are these advancements mostly going to benefit those big corporations and government agencies?
The benefits of these advancements will be felt across many industries and applications. Faster, more realistic video games, of course. But we're also talking about more sophisticated medical imaging, more accurate weather forecasting, more efficient energy grids, and even self-driving cars that can actually navigate without running over pedestrians.
Okay, now you're talking my language.
Yeah.
Self-driving cars that don't try to kill me. Sign me up. But seriously, it sounds like GPUs are going to be at the heart of some pretty major changes in the years to come. It's exciting, but also a little bit scary, Who knows what the future holds? Maybe our GPUs will become so powerful they'll start writing their own deep dives and put us out of a job.
That's an interesting thought, but I wouldn't worry too much. After all, who would write all the snarky jokes and irreverent commentary?
Touché. All right, folks, that's it for our deep dive into the world of GPUs. We've covered a lot of ground, from their humble beginnings to their mind-blowing future potential. We learned about the different types of GPUs, the specs that matter, and the trends that are shaping the industry. But most importantly, we had a hell of a lot of fun along the way. And that's what it's all about, right? So until next time, stay curious, keep learning, and don't be afraid to ask those stupid questions, because you never know where they might lead you. Peace out, you magnificent bastards.